So today I want to recap some of the key points from Module 2. All right, so to recap some of the key points from Module 2, the first one, first question that came up a lot was, all right, what are electron domains? How do I count them? Um, so electron domains are just groups of electrons in a specific area around a central atom. And the way to count electron domains around an atom is just to add up the number of atoms it's bonded to plus the number of lone pairs it has. And so the key point there is if you have a double bond or a triple bond, that just counts as one domain because all those electrons have to be grouped in the same area. So since we're dealing with molecules that are always going to follow the octet rule, um, or at least never go over the octet rule, the maximum number of electron domains we're going to deal with will be 4, or it could be 3, or it could be 2. So just to give an example of each of those. There's carbon with 4 domains, there's nitrogen with 4 domains. Whereas here's an example where carbon has 3 domains. So you count the domains by looking at how many atoms it's bonded to, plus how many lone pairs are around it. So then you might ask, well, why do I care? Why does this number mean anything? Well, when we're trying to figure out what shape an atom is going to have, we generally think about trying to get the domains as far apart as possible. What is it about electron domains that would make them try to get as far apart as possible? They repel each other. They're negatively charged. So we try to get the domains as far apart as possible. So it helps us to count how many there are and then figure out geometrically what does it mean to get them as far apart as possible. So we come up with 2 different kinds of geometry. One is what we call electron pair geometry. One is what we call molecular geometry. So electron pair geometry is the geometry that describes the relationship among all the domains. Like we said, we focus on trying to get them as far apart as possible because they repel each other. So just to give an example, one that I already discussed was NH3. For NH3, nitrogen has 4 domains. And the question is, how do I get 4 domains as far apart as possible? Well, at first, most people think about this and they say, well, you could make just like a plus sign. But that's if you're imagining a flat universe. In 3 dimensions, you can actually get further apart than just a plus sign. And so the shape that gets the 4 as far apart as possible is called tetrahedral. In a tetrahedral geometry, you have 4 things coming off the central atom. One of them comes towards you and one of them goes away from you. So the way we note that as chemists is we draw a wedge bond when something is coming out of the page toward you. And we draw a dash bond when something's going into the page away from you. Now, tetrahedral geometry is the only one that's going to require us to do this in this course. The other 2 geometries are just flat. They can be drawn in a page without actually using wedges and dashes. So nitrogen has 4 domains. It's going to have tetrahedral electron pair geometry. Sometimes we only care about where the atoms are and not where the lone pairs are. And so we have this separate term that we call molecular geometry. Molecular geometry is the shape that describes the positions of just the atoms if we imagine that the lone pairs are invisible. Not that the lone pairs don't exist, but that they're just invisible. You don't see them. So going back to the example of NH3, if NH3 is tetrahedral, but one of those positions is occupied by a lone pair, if I imagine that lone pair is invisible, so here's my tetrahedral structure. It's got nitrogen in the middle. It's got 3 hydrogens around the outside. And then one of the spots is a lone pair. To get the molecular geometry, I'm going to make my lone pair spot become invisible. So I make that invisible and I'm left with a different shape that basically has 3 legs that point down. So this would, you could sit this structure on a table, and I encourage you to take out a model kit and build it if you've never done that before. What would you call that shape? All right, you could call it a trigonal pyramid. That's the official name it's often given, so the molecular geometry. Trigonal pyramid. Or if you didn't want to say trigonal because it just sounds weird, you could say triangular pyramid. Or you could just say tripod. So that's the distinction between electron pair geometry and molecular geometry. Questions about that? Yep. Yep. Just a request to go back to the other slide. So in the Module 2 resources, there's a chart that basically has all the 5 possibilities for geometries that you'll deal with in the class. So I encourage you to fill that out. There's a filled in version and a blank version. You can start by trying to fill in the blank one, and then look at the filled in one. But basically, you just got to know those few geometries. So the second key part of this module was about charge distribution. So where charges are in a molecule. Turns out that has huge effects on the way molecules interact with each other. Partial positives in one molecule are going to attract partial negatives in another. So we start by thinking about bond polarity. And for bond polarity, the key is just when atoms share electrons, they don't share equally. So covalent bonds equal shared electron pairs between atoms. But they're not usually shared equally. Usually one atom pulls more strongly on the electrons than the other, and that makes the bond polar. So when one atom is more stronger than the other, it pulls the shared electrons closer. So for example, in NH3, which we just looked at, we have nitrogen bonded to 3 hydrogens. So how do I know which one's stronger? Nitrogen or hydrogen? Just look on your periodic table. I gave you the electronegativity values, so use the periodic table. A lot of people made mistakes on the skill checker just because they didn't look at the periodic table. So if you look on the periodic table, and we're comparing nitrogen to hydrogen, in terms of electronegativity, nitrogen is, I think, 3.04. Hydrogen, I think, is 2.2. So what that tells me is nitrogen is definitely stronger. So in terms of polarity, what that means is in each of these bonds, the shared electrons get pulled closer to nitrogen. And sometimes we represent that by drawing little arrows to say, all right, the electrons are getting pulled closer to nitrogen. And what we do with our arrows, a lot of times we put a little plus sign at one end of the arrow to show that that's the end that has extra positive charge left behind. Because if nitrogen's pulling the electrons closer to itself, that's leaving behind more positive charge on the hydrogens. So in this case, hydrogen gets a partial positive charge, and we indicate that with a little letter delta and a plus, and nitrogen gets a partial negative charge. This symbol here, this is a lowercase delta. And we use that to indicate partial charge. So you always want to be thinking about polarity. When you look at a molecule, you see differences in electronegativity, think, where are the partial negatives, where are the partial positives? All right, questions about bond polarity? All right, so then the next layer of bond polarity is what we call the inductive effect. So the inductive effect is this. When you have, what do you think the word inductive means? Any idea? The root word here is induce. What does it mean to induce something? To make it happen. Well, I don't know. You could imagine someone saying like, well, I didn't cheat on the test, but I induced my friend to cheat on the test by holding my paper right near her face. Yep. Ah, yeah. So in medical terms, when you look at the side of a package of something that might be poisonous, it says in case of swallowing, induce vomiting. So that means cause someone else to do something. So to induce something is not to do it directly, but to do it indirectly, make someone else do it. What the inductive effect is when you have an electronegative atom pulling on electrons, it then induces the next atom in the chain to become effectively more electronegative. So imagine we have carbon atoms bonded to each other in a chain, and there's some chlorine atoms bonded to one of them. chlorine is highly electronegative. So what chlorine does is it pulls on the electrons in those bonds. And that makes that carbon really partially positive. So this carbon here, I'll make this carbon red. That red carbon becomes very partially positive because of the effect of the negative, because of the effect of the electronegative chlorines. So now, in the carbon-carbon bond, we would normally think, well, carbon-carbon bond is two of the same atom. No one's stronger. They're both equally strong. So that should not be a polar bond. But what happens now is this red carbon becomes stronger than it was before. Because it's got a partial positive charge, that means it's going to become more attractive to the electrons in the next carbon-carbon bond. So if I draw that next carbon-carbon bond blue, the electrons in that carbon-carbon bond are now going to get pulled towards the red carbon. So the red carbon has been induced to become more electronegative than it otherwise would be. So this bond now becomes a polar bond, which we wouldn't have expected before. And then the next carbon would kind of pass the effect along, but that effect actually would get weaker with every bond. So now if I go over here and make this green bond here, that's going to become slightly polar, but it's going to be a little bit less. So every time you go through this induction process, it gets a little bit weaker. So the inductive effect is the idea that an electronegative atom can induce its neighbor to become more electronegative. And it's basically pulling on electrons in those bonds, going all down the chain. Are there questions about that effect? All right. So I do want to make the point that effect gets weaker as you go down the chain. So with each atom in a chain, the inductive effect is weaker. So if you had a fluorine at one end of a chain that's pulling the electrons towards itself, the next carbon would be induced to pull on this carbon-carbon bond a little more. The next carbon would be induced to pull on this carbon-carbon bond a little more, and so on, but the effect would get smaller and smaller as you go down to the chain. So by the time you get over here, there's very little effect. On this end. Tommy. Oh, so the question is, does it have to be a chain of the same atoms? No. So this effect can be felt even if it's not just carbon to carbon, carbon and nitrogen, any atoms. The inductive effect will take hold. But the more atoms you have to go through, the weaker it gets. It's like playing telephone. You remember playing telephone? Like the signal gets weaker every person it passes through. The message gets a little more jumbled. The inductive effect gets weaker the whole way through. And then the last thing I wanted to talk about was something that very few people understood at first. Maybe it wasn't even addressed in any of the resources, so I'll talk about it here. The effect of formal charge. So the question I want to ask is, how do you think positive and negative formal charges affect how electronegative an atom is? So in other words, which nitrogen pulls more strongly on electrons? In those two molecules I drew. Well, what does a positive formal charge mean? When I put a positive formal charge on an atom, what does that mean about that atom in that structure? Yeah, it's effectively lost an electron. So, if something has lost an electron, it's got a positive charge. How do other electrons feel about it? Electrons have what kind of charge? Negative. So electrons are going to be more attracted than they were before. So a positive formal charge is going to make an atom more attractive to electrons, which means it makes it effectively more electronegative than it normally would be. Okay? So, key point here, electrons are attracted to positive charges. So nitrogen with a positive formal charge pulls more strongly on electrons than nitrogen with a neutral charge. So in terms of these, the hydrogens on the nitrogen with a positive formal charge are going to have bigger partial positives than the hydrogens on the neutral nitrogen. The reverse is also true. If something has a negative formal charge, that makes it effectively less electronegative than it normally is, because electrons aren't going to like it as much if it's got a negative formal charge. So So if we were comparing, say, NH3 to NH2 minus, now the hydrogens in NH3, they've got a partial positive charge. The hydrogens in NH2 minus, their partial positive charge would be really small. So formal charges can affect polarity. And that idea will come up again, how formal charge affects electronegativity. So this isn't the last time that idea will surface. Are there any other questions about anything from Module 2? Yep. What's the difference between linear and bent? So going back to geometry, the difference between linear and bent is for linear, it literally means a straight line. So we have a molecule like this. Here there are two domains. For each carbon. And when you have two domains, how do you get two things as far apart as possible? Well, they have to be directly across from each other. So this would be linear. For something to be bent, that essentially means not straight. So when you have, say, oxygen with two lone pairs in water, this has 4 domains. So the electron pair geometry is tetrahedral. But if we imagine the oxygen being tetrahedral, tetrahedral looks like this. So if I put the 2 hydrogens here and put 2 lone pairs on the other 2 domains, and then say, okay, for the molecular geometry, I'm imagining the lone pairs are invisible. So here, let's make them invisible. Ready? Bye-bye lone pair. So then I say, all right, if the lone pairs are invisible, now it's got bent molecular geometry because the 2 things are not directly across from each other. Any other questions? All right.